Hello, and welcome to this presentation on nonlinear optimization. This content is part of Gurobi's Opti 202 course for data scientists. My name is Dan Steffy, and in the next 30 minutes, I'll give you an overview of some nonlinear optimization basics and show you how to model and solve nonlinear problems with Gurobi. Let's get started. We have 4 topics on the agenda. First, we'll introduce the idea of nonlinear optimization and give some intuition on why it is challenging. Then we'll survey a few application areas in which nonlinear optimization is important. We'll then move on to discuss some modeling basics, highlighting some different categories of models and discussing best practices. And finally, we'll demonstrate how to model and solve nonlinear models with Gurobi Pi. Our first topic is to introduce what we mean by nonlinear optimization. We will also have a look at why it is more challenging than linear optimization. Nonlinear optimization solves problems where the objective or the constraints are curved or complex, unlike straightforward linear equations. Here we have an example of some nonlinear objective functions with either one or multiple local optimal solutions. Nonlinear models can include quadratic, polynomial, or trigonometric functions, creating complex solution landscapes. The world is full of well-known nonlinear relationships across all industries, physical laws used to model real-world systems, or statistical measures used in areas like finance. The constraints can also be nonlinear, which can give additional challenges when searching for an optimal solution. Nonlinear models are often crucial for properly representing real-world systems with enough accuracy to make good decisions. However, they are not without their drawbacks. Challenges arise due to the possibility of multiple local optimal solutions and non-convexities, often requiring advanced algorithms to find globally optimal solutions. Some of the properties that enabled us to solve linear optimization problems efficiently also no longer hold. Let's take a moment to review some of the nice properties of linear optimization models. First, corner point solutions. Optimal solutions for linear optimization problems can always be found at corner points of the polyhedron, simplifying the search. Another property is that local optimal solutions are also globally optimal. So once we reach a corner point of the polyhedron and there's no cost-improving directions, we know that we're at a globally optimal solution to the problem. Another property is the simplicity of the constraints. Although there may be many of them, linear constraints form straight, well-defined boundaries, making the feasible region easier to navigate. We have efficient algorithms for solving linear programs. Solvers can use efficient methods like the simplex method or interior point algorithms, which are well suited to these linear structures. Overall, this leads to a lower computational demand when compared to nonlinear systems. Linear problems require fewer resources to solve, resulting in faster and more reliable outcomes. Of course, things will become more difficult, as we've seen, if we include integer variables, but including nonlinearities will significantly change the difficulty in other ways. Let's have a look at what can change when we include nonlinear objectives or constraints. First of all, we may find that we have multiple locally optimal solutions in different areas of the feasible region. This can complicate the search for and the identification of a globally optimal solution. Another thing that can happen is, in contrast to the case for linear optimization models, we may find that optimal solutions are lying within the interior of the feasible region, not just at boundaries or corner points. Another thing is that nonlinear models often have a complex, maybe non-convex landscape with peaks and valleys, making it challenging to find the best solution. Nonlinear constraints can also create intricate feasible regions with a complex structure, unlike straightforward linear boundaries. In all, this leads to a high computational demand. These intricate feasible regions may mean that optimal solutions may not be easily reachable from a given starting point. Solving nonlinear models often requires iterative, advanced algorithms, leading to longer solve times, everything else being equal. Similar to with MIP models, solving nonlinear problems involves breaking down the problem into smaller, more manageable pieces. With each step, the solver simplifies or relaxes parts of the problem, gaining valuable information. This iterative process brings the solver closer to an optimal solution or gains useful information, one step at a time. Users often include integer variables in their models as well, adding another challenge. We discuss these challenges because nonlinear optimization is complex. Luckily, the solver can handle them for you and can still deliver globally optimal solutions for mixed integer nonlinear programs. However, it's helpful to understand these obstacles so you can build models that the solver can digest as easily as possible. For nonlinear optimization, the structure of both the objective function and the feasible region play a big role in determining how challenging it will be to find the best solution. We can think of these structures as falling into two main categories, convex and non-convex. Let's look at an example of some objective functions, here where we are minimizing. An example of a convex objective function for a minimization problem is given on the left. One nice property it has is that if you can imagine dropping a ball into this bowl-shaped region, it would roll down to the bottom and it would always end up in the same spot, which is a global minimizer, no matter where it starts. In this particular case, there is only one lowest point, the global optimum, making it relatively easy to find the best solution. Algorithms can take advantage of this type of property. A non-convex objective function, such as the one pictured on the right, may have a more rugged landscape with hills and valleys. This means that there may be multiple low points, called local optima, and that the best solution, the global one, isn't always as easy to find. For example, imagine trying to find the lowest point in a mountain range. There may be lots of dips along the way, but there's only one true lowest spot across the whole range. This type of structure necessitates more complicated and intensive search algorithms. Next, let's look at some feasible regions. A convex region is one where if you pick any 2 points in the region and draw a line segment between them, the entire line segment will lie entirely within the feasible region. Although it may have a curved boundary, this property of convexity can be helpful for many algorithms. A non-convex feasible region, such as the one in the bottom right, may have a more complex shape, with possible dents and gaps. If you pick 2 points inside this region and draw a line segment between them, part of that line segment may fall outside of the feasible region. Think of it as an irregular shape, like a crescent or a winding path with twists and turns. This type of structure complicates the search for optimal solutions. For example, recall the simplex algorithm. It operated by pivoting from one vertex to other vertices inside of the feasible region, always traveling along straight line segments, all of which were contained inside of the feasible region. This type of search would no longer be possible inside of a non-convex region. Summing up, for convex models, the feasible region and objective curve are shaped in a way that all the local minima are global minima, making it easier to solve. Non-convex models can have multiple local optimal solutions, making it more challenging to find the global optimal solution, as algorithms, unless designed otherwise, might get trapped in these local optima. Additionally, many methods that are used to solve convex problems use the knowledge of convexity to tighten the bounds or find feasible solutions and speed up convergence. By nature, a lot of these methods only work on convex problems. Understanding these distinctions can help us recognize why some nonlinear problems are more challenging than others. We've spent some time exploring what nonlinear optimization is and why it can be so challenging, which might lead you to wonder, why go through all this trouble? Why bother with nonlinear optimization at all? Well, here's where the real story begins. Nonlinear optimization is crucial because the world itself is nonlinear. Take, for example, this colorful bear in the picture. It's fun, vibrant, and definitely resembles a bear, but look closely. Its shape is made up of flat, linear facets. Each one is a simplified approximation of the curves and detail of a real bear. Now, this bear looks good. We can clearly identify it as a bear. But if we needed an exact replica of a real bear, capturing every curve and nuance, this linear approximation wouldn't be sufficient. Just like this, in many real-world problems, simple linear approximations just won't cut it. Nonlinear optimization allows us to more accurately capture the complexity of the world and arrive at more accurate solutions. Now, let's dive into some examples of how nonlinear optimization makes a difference in real-world applications. As our first example, let's consider the finance sector. Quadratic functions in portfolio optimization have been around for a long time and are used to quantify risk. However, here I wanted to highlight yet another area in which an even more general nonlinear function is used, namely the estimation of market impact for trading applications. The idea here is that if you have the ability to move huge amounts of stock or other assets around, for example as a large institutional investor, you can't just take the current buy and sell price and multiply it by some large number of units. This is because when you make those large trades, your actions are going to have a market impact, changing the trading prices of those assets. And you need to have a curve that reflects that impact and estimates the change in the price you are going to create. The formula given here is commonly used to measure this market impact. Next, let's look at energy systems. Here we may be modeling the behavior of electricity or natural gas as they flow through a transmission or transportation network. All of these abide by physical laws, many of which are nonlinear. One specific application is the AC optimal power flow problem. Here, AC stands for alternating current, and therefore we are using sine and cosine functions to model the behaviors of the power flow, necessitating the use of nonlinear functions. Next, let's talk about oil and gas, where again, well understood nonlinearities in the underlying physical systems must be modeled accurately. Blending models to ensure that a product is on spec often use bilinear and quadratic terms to relate original qualities to the blended qualities. Nonlinear reaction rates may include exponentials and powers to model how a reaction may change with respect to different temperatures and pressures. We'll go through an example of how to model reaction rates in the exercise set. When modeling heat exchangers, we need to model how heat will be transferred between streams of different temperatures. The log mean temperature difference formula is shown in the slide, which includes a quotient and logarithms. This quantifies how heat is transferred between a hot stream and a cold stream, and this is important for heat network design. In fact, many fundamental contributions to the field of nonlinear optimization have been made by chemical engineers as they have worked on problems such as the ones that I've just described. Finally, we'll talk about engineering in general. Engineering is another area in which nonlinear relationships arise, again coming from the physical properties of the systems being considered. They could represent things like gravity, torsion, pressure changes. For example, one application is the design of truss structures for bridges or other structures, which can often be modeled as nonlinear optimization problems. By now, we have seen that we can incorporate nonlinear objective functions and constraints into our optimization models. We have also seen that there are many real-world applications where we really would want to do this. Next, let's have a closer look at some of the categories of nonlinear models and discuss some best practices for modeling. Not all nonlinear models are created equal in terms of the difficulty. And among problems of the same size, the following categories will give you some idea of how difficult your model will be to solve. In this slide, I'll start by listing some of these categories, and then in the upcoming slides, I'll dive into a bit more detail on how you would identify which category your model falls into. So the first of these is convex quadratic objectives. So this is a kind of model where basically you have linear constraints and the only nonlinearity you have is a quadratic objective function that's convex. So this, among the nonlinear models, is generally the easiest to solve. Next, we have convex quadratic constraints. Again, we've talked about convexity in some of the earlier slides. This becomes a little bit more difficult when you have convex quadratic constraints compared to only an objective function, but it's a little bit harder. Next, we have non-convex quadratic. So this is where our objective function and our constraints still are quadratic, but have some non-convexity. And this becomes a bit harder and necessitates some challenging search algorithms. And then finally, the fourth category is basically anything goes, general non-convex. And this is our most complex type of model. And here we can include all kinds of different nonlinearities like sines and exponents and things like that. And we have to rely on some more involved algorithms to find the global optimal among those constraints. The first category of models that we're considering are models that are having a convex quadratic objective function and linear inequality constraints. These are the easiest among the nonlinear models to solve, given the convexity and the fact that the nonlinearity appears only in the objective function. How would we know if we have such a model? Well, first of all of our constraints should just be linear inequalities, just like a linear program. And our objective function has a quadratic term with a matrix Q that's positive semi-definite, which satisfies the following property listed on the slide, simply that x transpose Q times x is non-negative for all vectors x. So these would look like the functions as pictured here. So for example, if we have just one variable, we would have a parabola, but in higher dimensions, we would have a shape like this that's convex. The next category of models would be ones in which we may also have convex quadratic constraints, such as the pictured region below. So having quadratic constraints can increase the problem complexity, but it's still easier than the other non-convex models we'll discuss in a moment. So models like this have a specialized barrier algorithm that can solve quadratically constrained problems. And how do we know if we have a convex quadratic constraint? Again, we'll be relying on the same property of the matrix Q, that it's positive semi-definite. The next category of models we'll consider is considerably more difficult. And this is the first type of model we've looked at where we have non-convexity. So these would be models where we may have an objective function where the matrix Q is not positive semi-definite. So for example, as we have pictured below, or we might have quadratic constraints, again, where the matrix defining them is not positive semi-definite. And in this case, we end up with non-convexity. Or additionally, it would be the case for any matrix Q, even if it's positive semi-definite, if we have equality constraints, and we have something pictured like this on the right, if this is the feasible region, you would see that this is also non-convex. So non-convexity in constraints or the objective now allows for us to have multiple locally optimal solutions. And this considerably raises the difficulty of solving the problem, as we've discussed earlier in this presentation. So for this, Gurobi utilizes a spatial branch and bound algorithm with specialized node relaxations to solve these models. Finally, we can talk about general non-convex. So these are the most complex types of models, and they require specialized global methods to handle the nonlinear terms. So some examples of these include some of the examples I've highlighted in the previous example section. Again, we will use spatial branch and bound and solve our convex node relaxations. So here we may include a wide variety of different functions like exponentials, logarithms, trigonometric functions, and more. And in the pictures here, this illustrates what we might have for a feasible region or for an objective function. And you see, by including these additional nonlinearities, we end up with much more complicated structure, possibly allowing us to have multiple local optima, and also just generally a more complex structure that's more difficult for our solution algorithms to navigate. All right, now we've seen that there are many different types of nonlinear models. So let's move on to talk about some general best practices. And I'll sum this up in the sentence: to treat your nonlinear expressions with care. So the first point is, when possible, try to avoid unnecessary nonlinearities. Of course, if your model calls for a nonlinear function, this is what we're talking about, you should include it in your model. However, when you have nonlinear functions, you can look at them and try to figure out if there's a simpler way to represent them to reduce the amount of nonlinearity or possibly eliminate it. So for example here, we have the constraint that x over y is less than or equal to 1. And maybe if somewhere else in our problem we know that y is non-negative, then we may be able to simply multiply through by y to obtain a linear inequality, x less than or equal to y, which would then, in this case, eliminate the nonlinearity. So doing things like this is generally always going to be a good idea. And of course, this will depend on your model specifics, but I would say to look at your nonlinear terms and try to think if there's ways you can simplify them, reformulate them, just to reduce the amount of nonlinearity present in your model. Another important point is to provide good variable bounds. And this is especially important for some of the underlying algorithms. So for example, instead of providing an unbounded variable, if you know bounds on the variable based on your knowledge of the problem or other information, you should always provide those to the solver. These can help to reduce the search space and allow for better initial approximations of the nonlinear functions. Another important point is scaling. So for example, choosing the appropriate units of measurement in order to reduce large coefficients in your model. So as has been discussed in some of the other presentations, even for linear models, having a well-scaled problem is important. And for nonlinear models, this is even more important. So scaling your problem to have to avoid data with very large or very small orders of magnitude, or large and small numbers appearing together in the same constraint matrix, this will generally help your model to be more numerically stable and improve solver performance. In our final section, we'll have a look at how to model nonlinear relationships using Gurobi Pi. In this section, I'll be describing a new modeling object named NL expression, which allows Gurobi users to build compound and multivariate nonlinear expressions, which can represent the objective function or constraints in a model. An NL expression is constructed by performing arithmetic operations using Gurobi Pi objects or by applying nonlinear functions. A list of supported arithmetic operators includes addition, subtraction, multiplication, division, and exponentiation. On the right-hand side here, let's look at some examples demonstrating the flexibility of an NL expression. With this type of expression, you can now model compound nonlinear functions without the need to introduce auxiliary variables. Gurobi will construct expression trees behind the scenes. Note that Gurobi Pi will only store a nonlinear expression when necessary. Linear and quadratic expressions will remain categorized as linear and quadratic as seen in the examples. So for example, in the first expression, we just have 2 times x plus y plus z. This is a linear expression, and it will be treated as such. In the second one, we have a quadratic expression. When we multiply and add these various Gurobi variables together, we end up with a quadratic expression. But as soon as we start taking a product of 3 variables, it will be upgraded to Gurobi's NL expression type. Now, I want to mention that this function is brand new in Gurobi 12.0, which has just been released and allows for more sort of natural modeling of nonlinear expressions in Python. Beyond the list of overloaded arithmetic operators on the previous slide, NL expression also supports many nonlinear functions, as listed on this slide. These include several trigonometric functions, exponentials, square roots, logarithms, the logistic function, and the square function. These nonlinear functions reside in the NL-func module of the Gurobi Pi package. This distinction is necessary to differentiate Gurobi's nonlinear functions from similarly named functions in Python. On the right, we see various examples of constructing nonlinear expressions using these functions. It's also possible to build nested nonlinear functions where the argument of one nonlinear function is itself a nonlinear function. However, keep in mind that just because something can be modeled, it doesn't necessarily mean it can be easily solved. So as we see here in the examples, we can model the sine function, we can model cosine of x plus y, and we can build more complicated functions involving a compound of a log, square root, and more. Next, I want to make a note about how to represent nonlinear inequalities. Gurobi's Python API and the underlying C layer that it calls supports general compound nonlinear constraints of the form y equals f of x. The supported form requires that y is a single variable, the sense is equality, and f of x is a nonlinear expression. This means that it's not possible to directly write down a nonlinear inequality constraint. Therefore, to implement less than or equal to or greater than or equal to constraints, such as f of x less than or equal to c or greater than or equal to c, you'll need to define y as a resultant variable, where y equals f of x, and then set appropriate bounds on the y variable in order to enforce your desired constraint sense. So, for example, in the first case, f of x less than or equal to c can be represented as y equals f of x, and then setting y as a variable less than or equal to c with no lower bound. In the preceding slides, we've looked at how to construct nonlinear expressions in Gurobi. Now let's look at how to use those to build nonlinear constraints in Gurobi Pi. There are two ways to do this. So the first is to use the add gen constraint NL method. In this, you give it an input of a resultant variable and an expression. Here, the resultant variable should be a Gurobi variable object var, and the expression here should be any Gurobi nonlinear expression. And remember, the sense here will always be equality. Additionally, you can use our overloaded add constraint method, where you will have a temp constraint. And a temp constraint can be constructed by equating a single variable equals to a nonlinear expression. And again, we must use equality. Now let's look at a couple examples of implementing some specific constraints in Gurobi Pi. The first example involves implementing a nonlinear equality constraint of the form 2 times z is equal to x over y. The upper left box shows an intuitive but incorrect way of trying to implement this constraint. Remember, the resultant variable of add gen constraint NL should always be a variable object, whereas 2 times z is a linear expression object. You can use the add constraint overloaded method as well, but the constraint must also take the form discussed on the previous slide, where the nonlinear expression is equal to a single variable object. The correct way to implement this constraint would be to rewrite it as z is equal to 0.5 times x over y, with either method. In this case, we see that the resultant variable is a single variable z and is set equal to a nonlinear expression, and this will work just fine. Again, we can use add gen constraint NL, or we can use the overloaded add constraint method. The second example is an inequality constraint of the form log of x over y is less than or equal to z. Let's first review a couple incorrect approaches. The add general constraint NL method does not have an argument for constraint sense because it only accepts equality constraints. So if you try to tell it to use a greater than or equal to constraint here, it will result in an error. Similarly, when using the overloaded add constraint method, the nonlinear constraint should still be represented in the form y is equal to f of x. The correct approach here, as outlined on a previous slide, is to introduce a non-negative slack variable s and convert the inequality into an equality constraint. And then either method can be used to implement this constraint. So here you see we add s is equal to a new variable that would be non-negative by default, and then we can set z is equal to log of x over y plus this slack variable, either using add gen constraint NL or the overloaded add constraint, where we have z is set equal to the nonlinear function plus s. Let us conclude this section by reviewing a few subtleties of using Gurobi Pi to implement your nonlinear models. A first point is that Gurobi supports a specific set of nonlinear functions. It's a pretty long list, and you can use these to build compound nonlinear functions, offering you a wide range of expressive flexibility. However, we don't support arbitrary nonlinear functions, so you may find yourself in a situation where you have a particular nonlinear function that isn't very convenient to represent by building it up with the nonlinear functions we support. In these cases, you may find it worthwhile to, instead of using our nonlinear functionality, to build a piecewise linear approximation using our piecewise linear functionality. Another approach is to approximate a function using Gurobi's ML package. Another point is that since Gurobi 11, Gurobi has been able to solve mixed integer nonlinear programs to global optimality. The latest interface that I've described in the preceding slides is one that's new to Gurobi 12. So what this means is that we have a few different ways in order to represent nonlinear functions, and there's a few points worth noting. So one thing is that although our NL expressions allowed you the power to represent a compound nonlinear function and let Gurobi build up an expression tree representing those functions behind the scenes, Gurobi also allows you to build up your nonlinear function piece by piece using univariate general functions such as model add gen constraint xxx, where x is representing something like sine or cosine or power. In this case, you actually also have the flexibility to choose if the model is really solved as a mixed integer nonlinear program by controlling this func nonlinear parameter, or whether all of those nonlinear expressions are represented using piecewise linear approximations, which will then solve your model as a mixed integer linear program. So this is something worth considering, and although we will generally recommend to use our newest functionality, there may be reasons why you would want to experiment with the others. We are now reaching the end of the presentation. Let's quickly recap what we have learned. With nonlinear optimization, users can model and solve optimization problems with nonlinear objectives and constraints. We have seen several real-world applications where modeling nonlinear relationships is critical. We've also learned that there are many different categories of nonlinear models. Some are harder than others. And finally, we have learned how to incorporate nonlinear functions and constraints into our Gurobi Pi models. That's all for this video. I hope you have enjoyed the content and enjoy the upcoming content and videos in our Opti 202 course.